Hello and welcome to this quick demo video showing the new universal joint. I'm going to create a model. We're going to give it the name The Universal after the classic, albeit maybe a little bit sad song by the great British band Blur. All right. And we're going to call this a demonstration of the universal joint. Simple enough. Okay, gravity method, we're going to have it be our usual uniform gravity with a constant of 9.8. In the direction minus y. We'll do the duration of 5 seconds. And the rest we will leave as is. So there's our basic blank set of axes, and just as I mentioned, our first thing to do is go and check out our new universal joint. One thing I'll show is I've reconfigured the help menus to make them a little bit more concise and readable. That's just a little addition. That's not really part of the demo, but that might be something that you will check out. So we'll go ahead and add our new universal joint. The reference point and reference frame are the origin and the inertial frame. And we don't need to give it an initial angle, but I will do is give it a rate. We'll say the rate for this first joint, about the first axis is 1, about the second axis is 2, both of these in radians per second. And then for stiffness, I'm give them stiffnesses of 100, 100, and 200. I'll skip the damping and equilibrium. I kind of want this thing to just ring forever and ever, so I'll forget about the damping. Created that. We can see this extra frame here. Because I gave it the 0 initial value, we see it's equal to the inertial frame, at least at the beginning. So let's make it do something. We will give it a new body. I'm going to create a body using the rigid body box. So I'm going to call this... what do we want to call this? We don't need to call it anything. So we're going to keep it at the reference point being the origin, but attach it to the newly created joint, which is named A, or the newly created frame generated by the joint, which is called A. I'm going to give it a density of 2700, as if this is a piece of aluminum, a length of 0.5 meters, width of... let's see, we'll also do 0.5 meters for the width. And a height, we're going to have this be a thin plate, so 0.01 or 1 centimeter. What I want to do is attach this to the aft part of our created plate. Okay, we can see this plate got added. If we hit the play button, it'll derive our equation of motion and simulate. And we will see this guy wiggle a little bit when we hit play. Just as we can expect, it's basically a 2-degree of freedom oscillator because there are 2 deflection angles, and then the plate has inertia, so it's basically wobbling in 2 orthogonal axes. So next thing I am going to do to make this a little bit more interesting is I'm going to add to this, not in the classic menu, but in the joints menu, a rigid translation. So I'm going to actually add a second joint and a second panel. So we're going to start from the reference point at the origin, but what we're going to do is attach this rigid translation to the A frame. We're going to measure a distance of 0.5 in the x-axis and 0.25 in the y. Hit the check button, and going back to our model, what we can see is this blue point and vector at the corner of the panel that we just created. So the second thing I'm going to do, third thing I'm going to do is add another universal joint. And I'm going to attach it both to that point that we just created and the initial, or the frame created by the first joint. Keep the initial values the same. And then for the initial rates, we're going to give it a value of 3 and 4. And for stiffnesses, we'll make this a little bit less stiff than the first panel that we made. So 30 and 70, not going to work. So this second panel is carrying a little, or what's going to be the second panel when I create it, is carrying a little bit less total mass and inertia. So I'm actually going to assign a little bit lower stiffness as well. So we can see the second joint that's been created And now, if I go back into my bodies menu, I'll add a second rigid body box, attach it to the point created by the rigid translation and the frame C created by the second universal joint. Once again, I'll give it a density of 2700. It's a big aluminum plate. A length of 0.5. Same as before, but this is going to be a wider panel. Okay. Value of the created box must be non-zero. So that is warning me that I forgot to finish the definition. So going into the height, I'm going to call it 1 centimeter again, and similar to before, I'm going to attach it to the aft. Hit the check mark, go back to our model, see the second plate, go ahead and simulate. This one is more complicated and has, despite just one additional joint and one additional body, actually a much more complicated set of equations that it has to solve. So this is going to run a little bit longer. As I talk, I rotate around so that you can see this in a little bit better. And what I'll tell you about is what I've been recently working on for the past few days. That has been the documentation of MOMDYN and specifically creating a nicely formatted, modern-looking documentation website. So I will link that in the description of this video, and I hope you will check it out. And in a few seconds here, we should be able to simulate where you will be able to see the very dynamic motion of this two universal joint result. I just skipped ahead to the plots so you can see all that fantastic nonlinear vibration that we've got there. Maybe mostly linear vibration, but at any rate, what we see here, we have two universal joints, both get two axes of rotation, and by adding the spring behavior and the two panels, we get this dancing motion of the two. So, of course, one might ask, what's the practical purpose of doing something like this? Well, I'll tell you, this isn't just an abstraction. This is actually one way that you might think of modeling an airplane wing. So imagine if you had not just two panels like this, but you had a long section of linked together panels, each with a joint that allows it to basically flap and a second joint that allows it to twist. String together about 20 of those, and you got a reasonably good model for the vibrational dynamics of an aircraft wing. That's just one example. I'm sure all of you creative types out there could think of a few of your own, but I will conclude there. Thank you, and until next time.